This is a shortened version of a shortened version, so that I'm going to reduce my career into one slide, just to give you some background of what it was that I was doing for about 40 years till I retired, and then it turns out that I am still doing those kinds of things, so I never got it out of my system. And you might say that there are two themes that represent the kind of work that I do. And I'm saying this mainly to try to put it all into context, because I'm going to be talking about the Ebola disease. That's the last item shown there. But I start out by saying that mainly I dealt with developing spatial autocorrelation statistics. I was mainly interested in the analysis of geo-referenced data on maps. Could be remotely sensed data, it could be just nice little maps that you could have drawn from some data that you had. And I have developed with others various kinds of statistics to study spatial autocorrelation. And what we're talking about is the way in which units on maps having values are correlated. And so we call it spatial correlation. Since they're of the same variable, we call it spatial autocorrelation. So I have something called a G statistic that's out there. There's an O statistic, an H statistic. Each one is doing something else in the same area. And I worked for many years in what was called pattern analysis. That is the kinds of point patterns, line patterns, or area patterns you might see on maps. There's usually some hypothesis that represents how that pattern evolved, and we test it in one way or another for whatever it is that we're interested in. I worked mainly simultaneously on a number of different kinds of, you might say, examples. And the example list really goes on for quite a while, but I've listed the disease area because I'm mostly interested in that today. And I worked in the 80s on SIDS. I identified, for example, that in North Carolina with SIDS, at an early stage, it was thought that the occurrence was random in the counties, the 99 counties of North Carolina. When you use the Getis G statistic as a spatial autocorrelation statistic, it shows that there's a cluster in one particular part, which I thought was useful, and some others did too. HIV, dengue, I spent quite a bit of time in those countries studying the distribution of disease there, and the disease was dengue. And a lot still has to be done with the disease. There is no vaccine that is useful yet out there, so that one has to come up with all sorts of ways to control outbreaks, and our work is part of that literature. Women's health with Professor John Weeks. I did in Africa, and I'll show a little bit of that. And my main concern these days is with Ebola. You might say, well, it's all over, Ebola. That actually it's been declared not an epidemic any longer in West Africa, but I'm working on it retrospectively, trying to assess the way in which the disease started, generated, spread spatially, and so I'll talk about that. And I have a model. I'll try to explain the model without going on for too long. This is the local G statistics. There's no time to get into it, but the key symbol here is W. W is the spatial weights matrix. In this case, Wij is on a great matrix. It's the spatial relationship between an item I, or a place I, and a place J. And that's the spatial weights matrix, and that's what helps us study spatial autocorrelation. Here's a little bit of the work on dengue, a little. Here's the culprit, and you may have been reading about this culprit with regard to Zika, but Aedes aegypti is even in the United States. The female mosquito bites, and it carries viruses sometimes it doesn't. In the case of dengue, there are 4 different viruses, and outbreaks can take place with dengue 1, dengue 2, dengue 3 over there, dengue 4 over there. Here's an example in a little village in Thailand. We were studying female Aedes aegypti. We wanted to get a better hold on the spatial extent of the mosquito, which would of course tell us where the disease was most likely to break out. And those dark circles represent houses that had, or if not in the house, in the grounds around the house, had female Aedes aegypti there. And you can see that they cluster, and my statistics help me to identify the cluster. The cluster is there, and our job is to try to explain why the cluster is there. Is there something special about the houses in that area, about the people in that area, and so on. And many studies have been done to try to identify the kinds of places that the mosquito likes to breed and so on. So that's what that's about. Here is a study at a different scale, and I've worked at many different scales. This is at the scale of Iquitos, Peru, which is a much bigger city than one of the villages out in Thailand. And what it shows us here is that you might say the expected distribution in distance for the Aedes aegypti pupae is shown by this line here, which tells us that this would be a random distribution of those little mosquitoes. And what we found in the city of Iquitos, the distribution was way more clustered. And this is a distance measure in meters, and it tells us that they cluster at very short distances. That's the spatial filtering. This is jumping to another example. Something that got me into this area in the first place was I was very interested, as most of us were, in regression analysis at one time to do something where we have variables here and a dependent variable over there, and we try to explain them, so on like that. If you're using georeference data, you must be aware of spatial autocorrelation. If you aren't, if you're not concerned with spatial autocorrelation, it may creep into your study in a way that makes a number of your parameters misspecified. That is, that there is redundancy. If one of your points is here in the real world here, and another one of your points is right next door, the chances of those two observations being similar is very, very great. That is often not taken into account. It's amazing that it isn't. In those days, in the 1970s and 80s, when I was doing those kinds of studies, there were very, very few studies that took the spatial autocorrelation into account. Now it's there. It's now even in spatial econometrics, econometrics textbooks, where it wasn't even a term that was known in the 70s and 80s, until the 80s. And just to give you an example, let's say we're trying to explain the total fertility rate in Cairo. And these are the districts that we have data for. The total fertility rate, and you can see that the dark areas are very high. That is, it looks like it's the suburban areas, but it's very highly densified areas outside of the center in Cairo have very, very high fertility rates. The idea is to explain those. But to explain them without falling into the trap, we have to go on. Okay, this is spatial autocorrelation here, and I was going to explain that a little bit. I wanted to talk a little bit about Ebola. So what I'm going to just say, since I have a very short time, and we just want to stimulate some discussion, as you said, and what I'm trying to show here is that at the beginning, or let's say within the first couple of weeks of the Ebola epidemic in West Africa, it was people who were using what is called the SIR model, the S-shaped curve, predicted that there was going to be about 100,000 cases and perhaps 50, 60, 70,000 deaths. We tried to come up with a model that tried to show what interventions might do. And that's what this is all about. And so I'll just run through this to show, for example, here's week 1 of the epidemic. And each one of these represents a week's number of cases in the 3 countries of Sierra Leone, Liberia, and Guinea. And you can see that over time, we get away, eventually we get away from its origins at the intersection of the three countries. And one of the reasons why we get away from it is because there's transport. People are moving, migrating, not necessarily migrating, or going to the city for their goods and services. So the three cities of Monrovia and Conakry and Freetown capture the disease, and then there might be what you might call a second wave. So our model it's a two-wave model, has the urban, you might say, the urban outflow and the rural outflow. And we try to incorporate that into the model. And, we'll just go back, since I have 29 seconds, and show, this is the model that we developed. It's a variation on a SIR model, and it tries to take into account interventions. And so what we're doing is retrospectively looking at the entire disease, and you can see that at certain times we are able to predict fairly well what the number of cases. This is our model estimates. These were the actual number of cases in Sierra Leone, and that's one of the things I wanted to mention.
Thank you. Questions? Who has a Am I doing it? Okay.
Thank you. In your SIR model, you have a bunch of parameters. So which ones of those ones are actually computed from first principles? Which ones are actually fed to the data? Because there is a whole saying that if you give me enough parameters, I can fit an elephant.
Yeah, well, well, that's what we wanted to do, and is fit to the data because we're looking at it retrospectively. If we use the typical model with one parameter, it would just be a nice S-shaped curve. But we used what you might call an intervention parameter, which slows the process down and takes into account the fact is that the number of infectives is reduced by isolation of the people. I'd have to go through that from first principles to try to show how that's done.
Another question?
I'd just like to make a comment, Art, because you said that the epidemic is over, but what we know about Ebola is that there will be another epidemic, and so it's really important to know that this retrospective study is going to change our whole response when the next epidemic happens, right?
That's what we hope, and I think there's enough interest and intelligence out there to say that we have to react quickly, and we have to take into account the fact that we're trying to actually stop the transmission. And that's essentially what we're driving at.
I have a question. Oh.
So as someone who know nothing about spatial autocorrelation or anything about the disease, but someone who have keep up to date on the news. So what are the things when next epidemic happens, what should I tell my husband, my kids about this? What should they do?
Well, the very first thing you should find out is where it is. If you're in the same household where someone has got the disease, you're in big trouble. Mm-hmm. Okay. But clearly, I mean, a lot of people in this country, I wouldn't say took it lightly. It was in the news day after day. But we didn't feel threatened as the people there were threatened because of distance. The fact is, in a case of Ebola, it's bodily fluids, usually blood, that is transferred from one person to another. And with the virus within you, you might say, there are instances where the blood might come to the surface through the pores or in other ways through vomit and all the other kinds of things. The idea with it's a very dangerous disease that once it's transmitted, you're pretty sure that you're going to get it within a very short period of time, 2 to 17 days. And if it occurs, there are certain cultural, I mean, there's so much to talk about, but cultural things. For example, in Guinea, one of the cultural activities when someone dies is to cuddle them and take care of them and present them in a very respectful way. That was devastating. Another group that were very badly hurt were the actual caregivers. They, at first, were not covered enough. They thought a little bit of covering was fine. They'd be very careful. They're not with us any longer. Oh, I'm sorry.
Maybe one more then.
So my question is a variation on the two that you've just heard. How will the results of your modeling inform response to the next outbreak of Ebola? What will responders take out of your research to make their intervention more efficient, more?
That's, you might say, that's the reason we're trying to do something that will be helpful. And our approach is to try to introduce interventions, which are not usually in the models. And I think a very detailed model might include how infectives are distributed, whereas they were not, it was not considered in great detail before. There was a parameter for family size, that kind of thing. When you isolate a case and put it there, of course, the distance increases, the chance for transmission decreases, and so on. If we could make that more specific and get very close to what you might call the medical surroundings, I think we'll be in a position where people will say, okay, let's take a look at this model or use this model to try to forecast what the final result might be. As it turns out, even though great numbers of dollars were thrown at the disease, not right away, but within about 5 or 6 months, there still, as it turns out, there was, you might say, overreaction. Tent cities were built all around Guinea and Sierra Leone to try to make sure that there were enough beds for all of, they were never used. Okay.
Well, thank you so much. So one of the